next speaker. The presentation is going to be on body area networks, connecting things together around the human body. And the speaker is Jerald Yoo, who received the BS, MS, and PhD degrees from the Department of Electrical Engineering, KAIST in Korea in 2002, 7, and 10, respectively. From 2010 to 16, he was with the Department of Electrical Engineering Computer Science, Masdar Institute, Abu Dhabi, where he was an associate professor. And from 2010 to 11, he was also with the Microsystems Technology Laboratories at MIT as a visiting scholar. Since 2017, he has been with the Department of Electrical and Computer Engineering at the National University of Singapore, where he is currently an associate professor. Dr. Yoo is well known as a pioneer of research on low energy body area transceivers, systems on a chip, and biomedical applications. His current research interests include wearable healthcare BAN and ultrasound systems. He is currently serving as a IEEE CAS Distinguished Lecturer, and he was a past Distinguished Lecturer for the Solid State Circuit Society in 2017 and 18. He is also an Analog Signal Processing Technical Committee member of the IEEE Circuits and Systems Society. Before we get started, I just want to point out a couple of things. If you have any questions, I think we're going to save them until the end of the presentations. There will be a Q&A. There will be a couple of options for you to get a question to the speaker at the end of the presentation. You can either submit a question, a written question using your Q&A window, and I'll pick it up and I can ask the question. Or I believe you also have the option of verbally asking the question. So with that said, I would like to get started with our next presentation.
Hello everyone. In this tutorial today, we will be covering the body area network, which connects the things together around the human body. My name is Jerald Yoo from Department of Electrical and Computer Engineering from National University of Singapore. This is the outline of the tutorial today. We'll first look into the body area network types, in particular the body coupled communication, and we're going to look at mostly into capacitive coupling. And in that context, we'll first look into the human body channel as a communication medium. And then we'll move on to the interface between the electrode and the human body itself. After that, we'll look into the transceiver that utilizes the human body as a coupling medium. After the transceivers are done, we're going to see how we can connect them together to form a network. And there are different topologies to form that, and we'll look into the most optimized form of the network for the human body coupling. Lastly, we will look into some future directions utilizing the human body as coupling medium, not only in the communication but also in the powering. Before we move on, let's look at why we need to have the body area network in the first place. When it comes to healthcare, we are experiencing a paradigm shift from reactive to proactive management. Reactive means caring and curing health after we detect and notice abnormality in our health. On the other hand, proactive means we are going to actively seek for healthy state and not fall into abnormal state in the first place. Of course, in order to do that, we need to continuously monitor the health status for everyday life. During the everyday life, well, it's easy being said than done, but how can you do that? Well, the wearable healthcare using the body area network is a good candidate or platform for a solution. So, what is a body area network? Well, as the name speaks for itself, it's the network that covers the body area. And if you compare with the other type of standards such as wireless LAN or wireless personal area network, in short, WPAN, the body area network has much shorter range. The coverage is typically less than 2 meters, and this makes perfect sense because most of a human being has height of less than 2 meters. Well, at the same context, the continuous monitoring reveals that the energy efficiency of the body area network is one of the key factors that we need to consider, as well as the reliability of the communication. Unlike the wireless LAN, we need to guarantee the quality of service in body area network. We may think that we don't need a separate protocol for body area network or BAN. It's because we can probably use Bluetooth or Zigbee or other existing protocols to cover that. But if you look at this graph, x-axis in the power and y-axis is data rate, you will see that Bluetooth and Zigbee are still, so to speak, those are the low power radio protocols, but they are still high power when it comes to the body area network applications, especially in the context of the healthcare. Those we need to have in healthcare and also in the medical field is that the data rate of no more than 1 megabits per second and the power consumption should be strictly less than 1 milliwatt, preferably less than 1 milliwatt, and definitely not over several milliwatts. And if you look at that, you will see that that field is still uncovered. And this is where we are trying to solve and we are to try to provide a solution for. This slide shows the requirements for BAN, especially in the context of healthcare. We as circuit designers typically concentrate on the phi layer efficiency in terms of the energy per bit. For continuous monitoring, obviously the energy efficiency is the key because of the battery lifetime, and that is related to phi layer. But if you think carefully, that's not always true. In other words, it's not only phi layer that affects the system level battery lifetime. We also have to think about the data link layer, or the MAC, for example, multiple access. Let's say even if you have the energy efficient phi layer, and we have two different sensors that access in the medium. One is requiring continuously accessing, and the other one only uses the channel 5 times a day. And if you use the contention access based protocol, for example, for the MAC, you'll be consuming a lot of energy throughout the day for those 5 times accessing per day type of sensor. You are trying to do the contending based access all the time, and you'll be consuming a lot of energy for data link layer. That's not efficient. Now, when it comes to the network layer, we have to guarantee the reliable connection, especially for the healthcare. So high reliability is also key. In the application layer, of course, the safety and convenience is another factor we have to think about. So as you can see, it's not only the phi layer we have to focus on, but we also have to pay attention to the data link, network, and application layer as well, especially for BAN. Noting that the BAN is to provide connectivity for the body worn sensors, let's look at what type of sensors do we have in the healthcare field. The first sentence that I would like to emphasize here is that the different sensors have different needs. The first type of the sensor can be classified as continuous reading and recording sensors, such as ECG, EEG, EMG, and etc. These sensors require the low energy operation because it's continuous 24/7, and also single or multi-channel recording is required. Now the second type of sensors are spontaneous. When I say spontaneous, you don't necessarily need to monitor 24/7 for every second, but you can actually do it several times a day, such as blood glucose, blood pressure, body temperature, and so forth. So these sensors can utilize the high duty cycling, and usually a single channel is more than enough. Now the third type is whereby the stimulating sensors, such as electroacupunctures, impedance cardiography or ICG, and so forth. So these sensors do require the high current drivability and so often requires multi-channel operation as well. So coming back to previous slide where I mentioned about the MAC layer or data link layer, if you mix these sensors up, the MAC has to do the diligence, otherwise you'll be consuming a lot of energy, wasting energy from there. look at the current band with the RF, typically having each sensor node with the battery, the radio will be RF radio will be forming a band. These sensors do have really good opportunity to, it's very intuitive and good opportunity to providing connectivity, very convenient, and number of nodes are very flexible. So typically, for example, Zigbee, you can have up to 255 sensors, but noting that we will unlikely have more than tens of sensors around the body, practically just unlimited number of sensor nodes. And also, because you are using battery, the power source is very reliable. On the other hand, there is a safety issue with the battery, meaning that what if you wear the sensor and then you have to take a shower? And also the potential interference is another factor that we have to think about. And also it's a bit difficult to form a multi-channel environment with such single node environment, single node configuration. So that said, this type of RF-based band is suitable more for the short-term monitoring and typically require single channels such as body temperature, blood pressure, blood glucose, and one lane ECG, for example. But there's a big issue with the conventional RF-based band. One of the limitations on the WPAN, Zigbee, Bluetooth, and so forth, all which is based on the RF, is having some fundamental limit on health monitoring band. The first thing is that 2.4 gigahertz in particular is very prone to potential frequency eaters. I say frequency eaters because the body, human body actually works as a blockage, unfortunately, for gigahertz region. From 1 gigahertz around 10 gigahertz, human body really absorbs a lot of RF energy. So let's say, we call it body shadowing effect. So let's say if you have the sensor TX on your chest and a receiver in your back. If you are indoors, there will be reflections from the wall and the communication will be maintained. But if you go outside, let's say in a field, it's not going to work because the TX power is not powerful enough to penetrate through the human body, which is absorbing energy. And you don't want that situation for healthcare sensors. Well, obviously, one of the solutions is to increase the TX power, but then it means that the battery will be drained very soon. So this means we need to have some complements. Okay, on top of that, on top of the body shadowing effect that we discussed in the previous slide, we also need to think about the antenna effect on the RF that is close in vicinity with the body, human body. We also note that the antenna placed just into the human body will give an additional 10 to 15 dB path loss, and the radiation pattern will change. And the worst possible case for body area network for RF will be, for example, binaural hearing aid, where you are connecting the one sensor node in one of the ears and the other sensor in the other side of the ear. Then there's no line of sight, and you have to penetrate through the human head, which gives the human head gives a huge blockage. Around 60 dB of attenuation is experienced. So how do you overcome that? Well, this graph also shows some of the problems, the data rate with the power consumption to overcome such. And we can see that the body-coupled communication actually provides a good compromise in the data rate with the power consumption. If you look more in particular, we can see that this slide shows the radiation pattern with the existence of the human body. You can see that the human body is actually changing the radiation pattern of the conventional antenna, especially when it's in close placement with the human body. The distance is around 0.6 centimeters in this simulation, in this paper over here. Compared with the free space, you can see that there will be a huge path loss and a radiation pattern change whereby the human body is existing. So this is why we need to think about some complements. So how do we overcome such issues? Well, one of such solutions, I wouldn't say this is the only solution, but this is one of the possible solutions, is to use the human body itself as a coupling medium. So background or the motivation is very simple. If the human body works as a blockage for the RF, can we actually use that as a communication medium instead of using it as let it be as a blockage? That's the motivation of the BCC. In short, we call it body-coupled communication. Well, the answer is yes, actually you can use it. And there are largely three types of BCC. The first is the magnetic BCC, whereby you're using magnetic coupling between transmitter and the receiver. So you'll be having a coil and you'll be transmitting the magnetic flux, which the coil in the receiver side will be detecting it, and changing the magnetic flux will be translated into data. Second type is the galvanic coupling, whereby you have all TX and RX both having two electrodes, as you can see, and you'll be utilizing the galvanic current from the transmitter to the receiver side. The third type will be capacitive coupling, which at first glance looks very similar to galvanic, but it's not. You can see that both in TX and RX only have one electrode connected to the body, and the return path will be formed by the parasitic coupling between the TX and RX PCB ground to the earth ground. So then this will be relying on the electric field. Each of these methods has its own advantage and disadvantage. So for example, the magnetic coupling is, I would say, very stable for the environmental variations, whereas you also have some limitation. You need to have the magnetic flux flowing through the body. That means that the form factor of the coil becomes an issue. So if, for example, RX is a watch form factor, you can embed the coil within the watch wristband. It's not a big issue, but this obviously has some limitations on different type of sensors that, for example, small form factor patches. Galvanic coupling also is relatively stable compared with the capacitive coupling. However, the existence of the TX and RX with both ground electrode and the signal electrode means there will be significant leakage from the signal electrode towards the ground electrode for both TX and RX. So the communication distance typically is very short. So if your communication distance is within, let's say, several tens of centimeters, perhaps this is a good choice. Now the third type, the capacitive coupling, can cover the whole body, entire body. That's a good news. However, because you're relying on the parasitic coupling capacitance for the return path, which obviously will vary significantly depending on your posture, depending where you are, depending when you're measuring it, which person you are, and the contact electrode impedance to the skin electrode impedance, they're all factored in the amount of the capacitive coupling. So this means the communication quality or the path loss from the TX to RX will fluctuate enormously, and that's the limitation. So you can see none of these are perfect solutions, so we have to choose appropriately. Now, we know that it's very sensitive. The capacitive coupling is very sensitive to environment, but this can be actually mitigated by the circuit. And we can also utilize the higher gain and higher data rate compared with the other topologies. So in this tutorial, we'll be focusing more on the capacitive coupled BCC. This slide very briefly shows how a capacitive coupled body coupled communication works. As I said, there's one electrode on the TX side and the other electrode in the RX side, and a return path from the RX to the TX will be formed by parasitic ground. Now, this means the channel path loss will be much less compared with the other two type of BCC. And biggest advantage I would say is that you don't need to have an antenna. And combined with the lower path loss means that the joule per bit, the energy efficiency, will be very, very good. Whereas on the other hand, the shortcoming of this is that the channel variation with respect to the skin contact or posture and all sort of environmental changes we have to deal with. So this type of BCC can be suitable for sensors in contact with the skin from the first place, such as EMG and EEG, which becomes very suitable option. Now, within the BCC, there are also having many efforts made to make it more ideal. So let's look at some conventional BCC transceivers, which targets several applications, which has the common problems, by the way, such as variable ground effect. I already mentioned the varying capacitance, return path capacitance results in this variable ground effect, and signal multipath, variable skin electrode impedance, high power consumption, and etc. So we have to tackle these problems at once. With that in mind, I have split this tutorial into 4 sections. The first is the channel itself for the capacitive coupled body coupled communication. And the second is the interface between skin and electrode, which result in the varying skin electrode impedance, how to overcome such or mitigate such variance. The third is the transceiver design that's suitable to the BCC, and also network, which will form the body area network out of BCC. So let's move on one by one. The first is the body channel. Since we don't have that many people who have done this before, we had to start from scratch. So when I first started this research around 10 years ago, we had to start from measuring the human body pathloss with only one electrode on the TX, the other electrode on the RX, and I started measuring the pathloss of the human body. Note that if you just hook up the RF generator on the one side and the receiver, the spectrum analyzer in the RX, then the pathloss you're getting will be very, very optimistic, which means that it doesn't reflect the wearable environment. Because if you do that, the RF generator is connected to earth ground by the wall-mounted power supply, and the RX is as well. So that means that the earth ground has a strong connection between TX and RX, means that the return path will be very, very strong. That's not the case for wearables. So in order to avoid that, we can insert the balloon that between the TX and the skin, and also the same balloon from RX to skin. Okay, even better is that if you can use the mobile or battery-operated TX and battery-operated RX, that's even better. But also note that if you have the large ground plane in the TX and large ground plane in the RX, that will also contribute to inaccuracy in the measurement. So having balloon is a good compromise. Now, what affects the channel gain? So we have investigated within the frequency, distance, body posture, movement, and subject dependency as well that have been studied to see what affects the pathloss of the human body. This line shows the measurement strategies whereby we started from the torso and limbs with a distance ranging from 5 centimeters, 15 centimeters, and all the way up to 120 centimeters. And subject was measured at an sitting posture. We fixed the same subject in the same location first, and then we expanded in different locations with a different posture with a different subject. And for tense measurements were conducted within the same posture, same subject, and same everything, and then averaged out. And we used the standard adhesive silver chromate electrode. And we also take into account the human head with the measurement within the human forehead from ear to ear measurement and head to limb as well. So here, this diagram shows roughly how we measured it. As I said, we have inserted the balloon from TX and RX as well. Of course, before we do that, it's very important that we remove the intercoupling of the measurement setup from the cables and electrodes. So we measure without the human body and then subtract that from the measurement. So then we can de-embed those intercoupling effects from the measurement. This slide shows the resulting BCC channel gain, or in other words, a pathloss. So if you compare with the RF transceivers, that results in around 60 dB pathloss from ear to ear because of the human head blockage, and also additionally 15 dB pathloss from small antennas. Those are the RF-based pathloss on the human body, around the human body. Compared with that, you can see that the channel pathloss for the human body coupling will be much less. So the shape itself is about the same. It has a bandpass characteristic from around 20 megahertz up to around 80 megahertz. You can see that the pathloss is minimum. So this is for, obviously depending on the posture of the human subject. We'll come back to that in the coming slides. Also measured with varying the distance and with different locations from torso to limbs or from head to head and so forth. You can see that all of them follow roughly the same bandpass characteristic from around 20 megahertz up to around 100 or 80 megahertz, I would say. And you can see the maximum channel gain results in around 50 megahertz, around 35 to 60 megahertz, and with the resulting path loss to be around minus 10 dB, which is very, very good compared with the RF on human body. We also check the channel gain variations for different measurements. So we measure 50 samples across the same TX power and measure with the same frequency and measure the variance. And as you can see, the histogram shows actually the gain variation is quite stable. So you can see that there's around less than 2 dB variations, around 2 dB variations only across the measurements. Of course, as I said, this is based on the same posture, same subject. So if you start moving around, the variance will be much larger, which the circuit has to do the diligence to compensate. In the previous slides, I said that one of the weaknesses of the capacitive coupled BCC is the variable ground, return path ground. And here we measured how serious that was. And we can see we were trying to vary the postures and also movement in location, electric position, as well as different subjects. And we can see that the channel gain may vary up to 20 dB. In the worst cases, it may vary even further. So actually, that's not a good news for the transceivers. So that's why the transceiver has to compensate. But for example, let's look at this case. You can see that there will be up to around 30 dB variations. And if you start moving around, and depending on if the electrode is loose or firmly attached, you can see that there's also variation. On top of that, there's interesting characteristic. Depending on different subjects, the path loss pattern also is different. Fortunately, within this subject, if you're in the same location, same time, same environment, it's quite stable, as we saw from the previous slide. However, if you change the subject, the path loss characteristic changes as well. All of them still show the bandpass characteristic, but you can see that depending on different subject, the path loss pattern is changing, and by up to 20 dB. So please don't misunderstand, interpret this graph. I'm not saying that the 60 years old or female of Asian will always exhibit this pattern, but it's the opposite, which means that different subject of different configuration will have different path loss characteristic. So let's summarize the body channel communication for the capacitive coupling BCC. What's the channel configuration or channel characteristics? We can see that the BCC is actually better than RF for on-body network. On-body is very important, which has around 20 to 40 dB less path loss. And capacitive coupling BCC is chosen because the path loss is minimized for 40 to around 80 dB, 40 to 120 megahertz bandwidth, but preferably below 80 megahertz. And BCC coverage can cover between torso, limbs, and head, which is virtually covering all around the human body. However, the capacitive coupling BCC must deal with non-idealities such as varying ground effect, varying skin electrode impedance, and multipath interference issues. Okay, so now we know the characteristic of the human body channel as a capacitive coupling medium, and we have seen the problems. Then let's now look at some issues, how to resolve the interface non-idealities, such as varying skin electrode impedance variation. For wearable sensors, we don't have to, but we can use the textile-based printed fabric circuit board, for example, which shows silicon on cloth with direct chip integration on the sensor itself, which will be naturally wearable. Now, it's very good in terms of flexibility and wearability, but it's a dry electrode. That comes with its own set of problems. All right. So why do we need to consider using the dry electrode? The reason is because as follows. The wet electrode, typically, for example, the 3M electrode you're seeing over here, silver chloride, is very good for short-term monitoring. But when you start monitoring it over long-term, let's say 2 or 3 days, some people will have skin irritation issues, as you can see. And also, more importantly, the as the electrolyte dries out, there will be signal degradation over time, which degrades the signal quality over time, which is not good for long-term monitoring. To overcome that, you can use as a complement the dry electrodes. So dry electrodes do have less problem with the signal degradation over time, but at the cost of much higher skin to electrode impedance. That's typically around 1 megahertz, mega ohms for 1 square centimeter, a 1 centimeter diameter. Noting that the noise in proportion with the electrode impedance, this is not an ideal situation. So to measure this, how serious the skin electrode impedance will be, you also have the setup here with the in-house made fabric electrode. So we also compare with the baseline 3M electrode, as you can see in the purple. And you can see that the absolute value of the skin electrode impedance is about order of magnitude higher for the same, around the same area, and that the black line shows it. And moreover, there's a stabilization time that is required. You can see that around 10 to 15 minutes stabilization time is required before the skin electrode impedance of the dry electrode stabilizes. Fortunately, the frequency response shape is similar to that of the 3M electrode. However, the fact that there will be much higher skin electrode impedance for the same area is still there. And this was measured after 20 minutes for initial stabilization time. So this means there is a need for us to monitor the contact impedance. Because the impedance varies over time depending on the skin electrode impedance, the signal quality at the receiver side will change abruptly. So this means we have to also monitor the contact impedance, skin electrode impedance, and compensate that from the RX. So how do we then measure this impedance? Well, there are many ways of measuring it. One of the solutions is to inject the sinusoidal or pseudo-sinusoidal current and then measure the voltage, which will be formed by the impedance of the RX side. Then you can measure the accurate amount of impedance. Now, that actually comes at the cost of generating the sinusoidal current, which is not easy. It comes at burning a lot of current or power. But for BAN, low energy or low power operation is one of the key limitations or key goals. So noting that, we have thought, is there any way we can actually minimize the overhead of impedance monitoring power? Now, one of such solution is to have the RC impedance monitoring, we call it. So noting that the skin to electrode impedance will be varying, and impedance means when there will be capacitance and resistance combined, there will be RC time constant formed. Now, if you have the same pulse generated from the TX, in the resulting wave that you can capture will be due to the RC delay having different rise time, as you can see from this figure. So small RC means that slew rate will be rising very high, much faster, and large RC means that it will be rising at very slowly compared to the small RC case. So depending on that, you can just measure the RC, the rise time of this waveform that you are providing to, and you can decide what is the relative skin electrode impedance. It's actually only measuring the resistance portion, but that's sufficient for roughly tracking the impedance situation. As a result, it only consumes around 4 microwatt in which constantly operating, compared with the references that generate the pseudosine sine wave. You can see that there will be drastic power reduction. This slide shows the result of the RC time constant based RC impedance monitoring. So to simulate the skin electrode impedance variation, we have inserted some piece of paper between the electrode and skin. So the higher the skin electrode impedance, the smaller the capacitance. So as you can see, the smaller the capacitance, the faster the rise time be. As you can see, if you have only 1 millimeter suspension from the skin to the electrode, you can see that the capacitance is relatively higher, that results in faster rise time. So they can roughly track the impedance situation in the RX side. Okay, now that we have looked into the first problem of the capacitive coupled body coupled communication, which was the interface skin electrode impedance variation, and we have overcome that by using RC-based skin electrode impedance monitoring. Let's look at some other issues related to the transceiver and how we can design and overcome such issues. Now, the first problems that we would like to tackle is the in-band interference, which can be mitigated by adaptive frequency hopping, direct switching FSK modulation, and DLL-based FSK demodulation. Within the BCC range, frequency range of 30 MHz to 150, or say 120 MHz, unfortunately there are many interference sources ranging from walkie-talkie, FM radio stations, and cordless phone. Because human body will work as an antenna as well, if you just let it be, these interference sources may interfere with the human body coupling, the communication itself. To avoid or to compensate this, we can use the frequency hopping. But if you just have a known priori interference source, such as, for example, if you're near to an FM radio station or a walkie-talkie, you can avoid hopping into that channel. This is a well-known technique called adaptive frequency hopping. And this can be utilized in BCC as well. This is the BCC transceiver architecture that exploits the direct switching FSK scheme. Conventional FSK modulators are not suitable for wideband frequency hopping system, as the VCO calibration overhead and limited loop bandwidth in the loop filter limits fast hopping. This will result in high power consumption especially at megabits per second region. However, in the transceiver shown, it uses the direct switching FSK instead with two dedicated separate PLLs. So at first glance, the TX seems to consume much more power than the conventional FSK modulators, as it has two separate PLLs. But that is compensated by not adopting up conversion mixers and using low carrier frequency, as most of the PLL blocks are simple digital logic. As a result, using the direct scheme will result in less joule per bit. Let's look at how the dedicated PLLs working for this frequency hopping scheme. This direct switching modulator solves all difficulties mentioned before by using two frequency synthesizers. The internal PLLs generate the frequencies representing the binary data 1 and 0. And one of them is switched to FS out at the rising edge of the reference clock. Now, this synchronized switching guarantees continuous phase at the frequency changing instant. Because the modulation is done by direct switching, the modulation speed is not limited by DLL dynamics. That's very, very important factor. And the loop bandwidth can be as large as possible, and the DC free coding for the modulate data and the calibration of VCO, which are the overhead for the conventional scheme, are not necessary. In addition, the internal PLLs generate much higher frequency than use a divide by 4 unit over here to get the desired FSK signal, which enables 4 times reference clock to be used, and the hopping time is reduced by 75%. The divider also requires the reference spur by 12 dB. The power overhead due to the additional PLL is controlled under 1 milliwatt. As a result, this modulator can achieve the fast FSK modulation and hopping time with less than 2 milliwatt power consumption. It's actually around 1.9 milliwatt. To reduce the power consumption, we can use 0IF FSK demodulators because you can directly recover the baseband. It reduces hardware cost. Now this slide shows the conventional demodulator and its limitations. As shown in this phasor diagram, the received data is discriminated by rotating direction of the I and Q signals. If it is rotating counterclockwise, it means data 0. If it is rotating clockwise, it means data 1. When every zero crossing of I and Q happens, you can determine the polarity of the other phasor, which tells the data which data has been received. Because of the simplicity, this has been implemented in many low-cost FSK radios. However, the problem of this scheme is the large zero-crossing delay. For example, when the data transition happens at this moment, you can see that the zero-crossing delay will be you have to wait until the next zero-crossing delay, which results in a large transition jitter, and we have to avoid this. To reduce the jitter, this DLL-based demodulator generates two additional signals, which are ID and a QD delay version. Now, these are pi divided by 2 delays which will be introduced to original signals. To synthesize the accurate delay, delay-lock loop structure is used, and a control voltage from DLL is applied to the VCDL replicas. This will generate QD phasor as well as ID, as you can see over here, which will reduce the transition jitter by half. Zero-crossing delay is reduced by half. As a result, around 40% reduction in total transition jitter is obtained with this simple scheme. By using that simple scheme, this slide shows the demodulated bit stream. So if you have tens of megabits per second, you can see with the conventional 0IF demodulator, the I is barely visible. Whereas if you use the DLL-based demodulator, the simple scheme that replicates the delay version of the I and Q phasors, you can see now the I is successfully recovered even at tens of megabits per second. Okay, so that brings us to the last challenges in the transceiver design of the BCC, yet it's the biggest problem in the capacitive coupling-based BCC. That's the varying environmental change and return path, which can be mitigated by the hybrid OFDM. Orthogonal frequency division multiplexing, or OFDM, is widely used to overcome the unknown or fading channels, which is perfectly adaptable for the BCC with the capacitive BCC, which has varying return path conditions, hence resulting in varying path loss. So this overcomes the signal multipath bicyclic prefix. It's very robust against the channel impairments. However, that comes at the cost of complex design, especially you have DACs and ADCs and power amplifier, which has to be highly linear. And it's very particularly difficult in the existence of the peak to average power ratio problem. We call it PAPR. In the OFDM, the PAPR is really high, meaning that the average power to peak power difference is very large, which has to be fixed, which has to be sustained by the DAC and power amplifier linearity. It means that the DAC and PA has to burn a lot of power to have large dynamic range. So that the conventional OFDM actually successfully mitigates the varying channel condition. However, that's at the cost of much more burning power. We can also see that the hybrid OFDM can overcome that issues of high power consumption. So how to overcome the PAPR problem in conventional OFDM, and how can you minimize the energy and area? Well, one way to do it is to just eliminate the DAC and the power amplifier, which, as I said in the previous slide, is the source of high power consumption in conventional OFDM. Instead, what you can do is that we can combine the baseband OFDM, which is the baseband expanded the bandwidth, and through the conventional FSK modulation. So it's not orthogonal anymore, but you're expanding more bandwidth. You're burning more bandwidth. So you don't have any ADCs, DACs, or power amplifiers, so no PAPR problem. And you compare with the conventional OFDM, there'll be around 50%, 60% area reduction. Of course, and it actually also mitigates the ground effect in signal multipath, but of course at the cost of large bandwidth. So for the conventional air channel, bandwidth is money, so it doesn't make sense to expand the trade-off with the bandwidth. However, for body channel, the bandwidth is relatively sufficient. You're not going to utilize the whole bandwidth for the body channel anyway, so you can actually deal with larger bandwidth. The way it works in the hybrid OFDM or pseudo OFDM is, as I said, you use the baseband OFDM signal generated and then transmit through the conventional FSK modulation. So each data bit over here has one wider bandwidth, and human body can sustain that. In receiver side, you're going to do the FSK demodulation and do the baseband demodulation as well to recover the data. If you compare the hybrid OFDM versus the conventional OFDM, the conventional analog method has smaller bandwidth, but it suffers from the high PA/PR problem, requires ADAC and ADCs in PA, which result in high power and area. Whereas the proposed digital or hybrid OFDM method is free from PA/PR. It achieves the mitigation of the channel impairment, but at the cost of larger bandwidth. But as I said, we can tolerate this in a body channel environment. This slide shows the BER performance in the simulation compared with the other modulation types. So for example, if you look at if you compare with the BFSK versus hybrid OFDM, you can see that the BER performance is improved. And if you look at the simulated and calculated, it's almost the same that we have achieved, you can achieve here. To further compare with the conventional scheme, if you just have the FSK only, which is denoted by the red color and black color over here, and red color is the 2-path FSK, the black color is the just FSK. If you compare that with the 2-path hybrid OFDM, you can see that the multipath is reduced. And for hybrid OFDM compared with the FSK, just the FSK, you can see that BER performance is improved. Both cases, the BER has improved much better compared with the FSK. So here are some measured results. The graph here is the simulation result, but the numbers are measured results. You can see that the hybrid OFDM, which this is the version 1 by the way, shows around 60% reduction in energy per bit compared with the RF transceiver on body, an average of around 70% reduction in BER. And it's also resilient across the 4-channel adaptive frequency hopping scheme. One of the important blocks in the hybrid OFDM block is that you have to actually generate the baseband OFDM signal. And the most power consuming block will be the IFFT and FFT block in a modulator and demodulator. So here, instead of using 64-point IFFT and FFT at once, we can combine two 8-point FFTs and 64 complex multiplications together. So instead of using 64-point at once, you're going to fetch the data in pair, insert in columns and fetch from rows. Insert in columns and fetch in the rows. That's the strategy here. And we can actually reduce the complex multiplication by 33% compared with just a mere Radix 2 implementation. And we can avoid using the 14-point multipliers and just use the binary add and subtract, which reduces the clock cycles compared with the conventional approach from 23 to 16 clock cycles. If you look at some other transceivers, by the way, these are mostly wireless-based approaches, you can see that the BCC transceiver mitigates the signal multipath, which outperforms the conventional FSK modulation, and also overcome the major drawbacks of OFDM. So frequency bandwidth is much lower in using the human body coupling. This version 1 uses hybrid OFDM with the adaptive frequency of FSK, and it actually mitigates the frequency multipath mitigation is done. Energy per bit is 1.5 nanojoule per bit. The power consumption is still slightly higher than 1 milliwatt, but it's low enough compared with the others. Data rate was 1 megabit per second. After we made the hybrid OFDM transceiver, we thought, what will be the constellation type that affects the BER performance? How would it affect the BER performance, in other words? So we did some simulation here to compare different type of modulation and constellation types, and you can see that out of these many operations, different modulation types, it looks like the BPSK actually offers the minimum BER performance under the context of the body area network using the body coupling. And also, the other thing was in the first version we used 64-point FFTs. Can we actually try reducing the number of subcarriers? So we found that by reducing the subcarriers from 64 to 8, there's minimal effect on the impact on the BER, whereas smaller number of N means simpler design, but at the cost of low data rate and higher clock. Typically, the low data rate will be a big problem in conventional RF, but since our data rate is targeting megabits per second, which is relatively low, this is not a big overhead. Higher clock may be an issue, but that depends on how we design the system. So that's where we developed the hybrid OFDM version 2, which has a scalable data rate. The version 1 has 1 megabit per second, but this one has 200 to kilobps to 2 megabits per second. So many applications can be covered. Now, this one is covering the PSK compared with the 8-point instead of 64-point FFT IFFT blocks to reduce the hardware cost. And also, previously mentioned skin electrode impedance monitoring system is included. And also glitch-free FFK modulation block is included. And also, again, the 4-channel adaptive frequency hopping is utilized. For FFT, 8-point FFT implementation, we can introduce the division by square root of 2, which means we can simply implement this as a shifter, scale and shift, instead of using floating point multipliers. So this will actually reduce the gate count significantly by 54% compared with the floating point multiplication. So the key is the divide by square root of 2 means that you can just scale and shift in the 2 to the power of n in binary. The measurement of the BER and SNR with different distances on arm, you can see that with this hybrid OFDM version 2 implied, around 70% reduction in BER is achieved versus just mere FSK modulation. And SR need to be over 2 dB for less BER result. This means that less than 120 centimeter communication distance is what the limitation of this will be, but that will be mostly sufficient to cover the body area. This shows the performance measurement of the transceiver version 2. You can see that compared with the simple FSK, there will be 2 orders of magnitude BER reduction, and it can tolerate up to 20 dB of channel gain variation. So that was the goal purpose of the hybrid OFDM, that the body channel communication, especially in capacitive coupling, is impacted largely by the channel gain variation, and that can be mitigated by this hybrid OFDM transceiver scheme. In the version 2 transceiver, you can also introduce the glitch-free FSK demodulation, where you have the variable gain LNA, which compensates for the path loss. So once you have detected the path loss, you can actually also compensate that in the LNA, and also variable threshold limiters and duty cycle correction to actually recover the full 50% duty. So you can see that from this measurement, depending on the threshold voltage for low threshold, it corresponds to the data rate of 0.2 megabits per second, where the high threshold will be corresponding to the data rate of 2 megabits per second to distinguish demodulation. This slide shows the chip die and power area distribution of the hybrid OFDM second version. You can see that the power of the FSK TX, FSK RX is evenly distributed. Hybrid OFDM baseband block is only occupying around 1% of the transmitter and receiver. Area-wise, however, the hybrid OFDM baseband is occupying a lot of area, as you can see, both in TX and RX, and FSK compared with the FSK part. You can see that the hybrid OFDM actually considerably takes a lot of area. the TX power is now meeting the target of less than 1 milliwatt, whereas the RX is still slightly higher than the target, which is 1.1 milliwatt, but it's around the same order of magnitude we have targeting for. For the data rate, it corresponds to 0.2 to 2 megabit per second, which covers a wide range of applications. And the sensitivity in the RX is minus 83.1 dBm. And BER at minus 78 dBm is 10 to the minus 7. This slide shows the FFT performance comparison of the version 1 and version 2. The version 1 was using 64 point, whereas the version 2 is using 8 point. As we can expect, the power consumption of the version 2, which is 8 point, is much less, 93% less power compared to the 64 point version. And the gate count is 70% less, which translates to less area of 86% less area. However, the higher clock is the pitfall, but even with considering the higher clock, you can see that power consumption is reduced significantly. So that's good news. Okay, this slide shows the comparison with the recent works in the body coupled communication in the capacitive coupling. And you can see that this latest version of the 8-point hybrid OFDM PPS using BPSK mitigates the signal multipath, mitigates the ground effect, and also skin electrode impedance variation is mitigated and achieves around 1.1 milliwatt in the power consumption in the RX. Area is quite small, less than half of square millimeters. In data rate is scalable from 200 kilobits per second up to 2 megabits per second. Okay, let me summarize the transceiver side. The BAN BCC transceiver. The very important message I would like to give here is that we should try to tackle the practical challenges in a body coupled communication BAN. Practical challenges will include the varying contact impedance, in-band interference, and most importantly, for the capacitive coupling, more in particular, is the varying environment return path problem. So these can be mitigated with the real-time monitoring of the impedance and adaptation, and adaptive frequency hopping for the in-band interference, and the varying environment return path and the path loss can be mitigated by hybrid OFDM. The hybrid OFDM is another name for the pseudo OFDM, which combines the OFDM baseband with the adaptive frequency hopping phi. It mitigates the signal fading and ground effect at the cost of more bandwidth, but as I said, for the context of body area network in the body coupled communication, more bandwidth is not a big limitation. It achieves lower BER versus the ENOV versus noise compared to the conventional FSK. Okay, that puts us to the last section of this tutorial, which is the network. So now we have looked at the channel and the interface skin electrode impedance interface variation, and also the transceiver that corresponds to the body coupled communication transceiver. We can combine them together to form a network to have a true body area network. For network, in the body area network, we can have largely two types of topologies. One is the simple star, where there's one base station with many sensor nodes, and the second is the simple ad hoc. Ad hoc means that there will be router nodes in between. So we can have the same distance from one base station all the way to the end peer node. However, in the ad hoc, there will be some routing relay network. Conventionally speaking, in the wireless sensor network or wireless transceivers, we prefer using ad hoc network because as the transmission distance doubles, the power consumption is increased quadruple, is square of the distance instead of linearly increasing. So to reduce the power, transmitting power, we have to have less distance as much as possible. So that's the motivation of inserting router nodes. However, is that true for body area network? remember the body area network, typically the distance, transmitting distance is less than 2 meters. And with the usage of BCC body coupled coupling, the path loss is much less compared with the wireless transceiver using around the human body. With that, I have done simulations here using the network simulator. And here the assumption is as follows. We have the RX threshold of minus 70 dBm, and we have continuous bit stream data every 0.1 to 0.4 seconds, and simulation time is 60 minutes. And here we compare the overall system energy consumption, which will be impacting the battery lifetime. So if you compare with the ad hoc versus the star topology, actually the star topology has much less overall energy consumption of the system. And this is because, yes, the transmitter's power actually reduces by 1/4 if you reduce the distance by half. However, in the body area network with the sensor nodes, the listening energy dominates, the RX energy dominates. So if you have more number of sensors, as in the case of ad hoc, the overall system energy will be much more, and that's not what we want. For the network configuration, we also have to design the packet properly, the length of the packet as well. So first of all, let's look at some vital signals, which is, I would say, one of the applications that the body area network is targeting for. If you look at various vital signals such as ECG, heart sound, heart rate, or respiratory rate, or even the temperature of body, you can see that there's a huge variance in required number of sensors. More importantly, the bandwidth as well as resolution requirement is very, very different. So that translates into different information rate. For example, if you compare the body temperature, you only require 80 beats per second, whereas for EMG, you need up to around 600 kilo bps. So as I said, for these, if you have to also have a proper MAC operation, and also the number of sensor nodes in the order of several tens means that we have to think carefully how to design a packet. So data packet structure can be designed in a way that you can vary the size of the payload because each application has different needs. Some applications like EMG has large data rate. You better off have a larger payload, longer payload. And also the PHY header, the header and the header as well as the footer as well as sync headers are overhead for the payload perspective. So you might want to have just the right amount of delay caused by the PHY headers. So by designing the sync headers with 20 bits, which is composed of preamble of 4-bit, sync ID 16-bit, and a length factor of 16 bits, and so forth, you can vary the payload length from 0-bit all the way to 4K bits. And that corresponds, there's a good reason we limit this packet size to 4 kilobits. Because we did the same simulation using the network simulator. Now the TX power is assumed to be 0 dBm, RX threshold is still minus 70 dBm, and the bit stream is still CBR, which is corresponding to the physiological signals. And we have calculated how much energy will be used with the packet size. Under such packet length, the payload length, if you have a shorter payload, you need to have more packets to transmit. If you have a longer payload, then obviously you need less number of packets to transmit the same data. And we can see that the packet length actually settles with respect to energy respect to the packet size. We can see that around 4K, around 4 kilobits, the energy actually settles down to some minimum optimum numbers. But whereas if you have too long packet length, then it will be a waste of energy as well. So this is why we can decide that probably around 4 kilobits of packet length is ideal for the body area network applications. Before we conclude this tutorial, I would like to show some future aspects and future directions of body area network, and one of such can be powering aspect. As the technology produces the miniaturizing effect, more and more wearable devices have been emerging. And so far, we have been concentrating on communication and networking aspect. But in the network also includes the powering. such like AirPods, wearable injectors, EEG devices, patches, and so forth. The big question that arises these days is how do we power them up? For example, no one wants to power up, charge 10 different devices, 10 different wearables every night. So battery is becoming more and more big overhead, and power delivery harvesting becomes an issue because current delivery and harvesting are not enough, especially for RF, for example, RF harvesting and power delivery, because of the same problem that body-coupled communication had, which is the human body blockage. They are not effective in the body area network context. Let us look at this slide as an example. Conventional RF power delivery approach suffers from the poor path loss in the body vicinity. Shown in the green curve, 20 dB path loss. Additional path loss is observed compared with the free space. And this is exactly the same topic I mentioned at the beginning of this tutorial. So this is due to the human body blockage. If you see, under more practical scenario where there's some body blockage, up to 30 dB more degradation will be expected, and this means around 30 centimeters apart from TX, path loss will be greater than 40 dB, roughly corresponding to the shaded area in the human body onto the left. So this making the RF delivery, power delivery using RF unfeasible, not feasible for the body area context. So for example, if you transmit 1 milliwatt, only hundreds of nanowatt can be harvested from the gray shaded area. And I mean in the best case scenario for the 30 centimeters. And in the gray shaded area, you cannot harvest at all. Now, we found that using the similar mechanism as in BCC, we can utilize the human body as a power delivery medium. As shown here, a TX can be placed in one location of the body, with the ground node floated, and has a parasitic capacitive coupling through the human body, to the earth ground. And we can also see that using this same mechanism as in the body coupled communication, we can deliver the power through the human body, and it can cover the whole entire body. The RS can be placed anywhere in the body. And if you can see from the graph here, compared with the 2.4 gigahertz in non-line of sight condition, for example, TX in the chest, RX in the back, you can see the body-coupled power delivery has much less path loss, around 20 to 50 dB less path loss. So now the power delivery through the human body coupling becomes feasible. Let's look at this example video as a demonstration. We are trying to transmit the power from one location, and this subject is going to grab the power transmitter. And then the calculator, which is powered off, battery is removed, will be powered up. As you can see, the calculator is now powered up, and now you're transmitting power through the human body. And you can see that the calculator is working properly. And as soon as you detach your hand, the power is removed from the calculator and the power calculator goes off. So this shows that the power delivery is also possible using human body coupling. So let us conclude today's tutorial. We have seen that the wearable band can be used for proactive healthcare. And you have to consider not only the energy efficiency of the PHY, but we also have to think about the convenience, safety, and reliability, which also has to be considered in the data link layer, network layer, and application. And out of 3 body-coupled communication types, we have extensively looked into the capacitive BCC because of its energy efficacy, but it also has some limitations in the ground effect as well as varying channel gain. So varying skin electrode impedance can be compensated. At the same time, the varying ground effect and the channel path loss can be mitigated by hybrid OFDM. And I have also said that not only the PHY layer, but we also have to take into account the network topology and system aspect as well. We have seen that under the body area network context, the star topology seems to be better choice in BAN applications. And also the packet length and these system aspect has to be considered. Lastly, as a future direction, we have seen that the body-coupled power transfer is a viable option, which complements the communication side. So the communication and powering can be under the same umbrella of the body area network. Thank you very much for your attention.
Okay, thank you very much, Dr. Yoo. That was an outstanding presentation. Really, I felt like I learned a lot about this topic, which is not an area that I work in so much. I do work on radios, but not so much on body area networks. This was an excellent presentation. So what I'd like to do now is open this up to questions. I did misspeak a little bit earlier at in the introduction of the talk. The audience members cannot ask their questions verbally. All right, so you need to submit your questions on the Q&A form, and I can read out the questions, and I believe Dr. Yoo is on the line, and he will be happy to answer them. So actually, I have a couple of questions. Dr. Yoo, on slide 12, when you were discussing galvanic coupling, I had a little bit of questions about the ground loop that could be introduced, particularly at the transmitter. What's actually prevent a ground loop from happening right at the transmitter interface, thus, basically taking all the energy from the receiver?
Chris, I got your question. Can you hear me clearly?
Now I can hear you clearly. Great.
So yeah, that was actually an excellent question, because the galvanic coupling actually is good in terms of the stability, I would say reliability in communication, as far as the communication distance is not that big as I described. And the biggest limitation is the distance, and the reason is just like you said, the ground coupling, the transmitter, the signal electrode, and the ground electrode are so close by in a way that the most of the energy is actually leaking through this ground loop. And you cannot prevent that actually. That's one of the limitations, and that's why the communication distance is actually not as far as the other two, which is the magnetic coupling and the capacitive coupling. But I would say, for example, if you're doing the body coupling through the body, inside the body, for example, from, let's say, implantables to the surface, then the galvanic current, although with this such big limitation on the ground loop, this is more viable option because, for example, the capacitive coupling doesn't work in implantable that well. So I would say there are trade-offs there. It depends on what your application is. You have to choose a proper, let's say, mechanism.
Very good. All right. That is interesting. I did not know that. Again, if there are folks in the audience who would like to ask a question, please submit your questions on the Q&A form, and we'll be happy to get those. I guess in the meantime, I did have a couple more questions. Sort of towards the end of your presentation, I don't know, it's probably about slide 76 when you're comparing the path loss, one of those slides that had the chart of the path loss of free space, and then then just inside the body. I didn't quite understand the last mechanism that seem to have an improvement of 20 or 30 dB in the body. So are you actually transmitting and receiving through the body? Is that correct, where you get this big improvement?
Oh, yeah. So let me first clarify. This is another excellent question here. First of all, what I was trying to first, can we show the slide? Let's say.
Yeah, that would be good. How do we? I don't know. Maybe if there's somebody on the line that's part of the team, if we could go back to about slide 76, 77, somewhere in there, I think that would be good.
I see one button here showing screen share. Let me see if I can share my screen. It has to install something here. Okay.
I don't think we have the ability to go back through the slides, I'm afraid, at this point. So.
Okay, so then what I can do is that, yeah, I can describe verbally. So what I did in that slide was the following. So I first compared with RF-based energy harvesting around the body. So for example, there are a couple of folks working on Wi-Fi based power recovery from the RF, and that was perfectly fine in free space. However, when it comes to body area, as I described earlier in the first part of the tutorial, that the human body is actually blocking significant amount of RF energy. So that, for example, if you have the power transmitter in your chest and then receiver is in your back, that actually significantly drops the efficacy of the RF-based power transfer. And that's what I was pointing out. And your question was, there was significant improvement in the blue line, which I showed as body-coupled based power transfer. And what I mean by that is, if you use the capacitive coupling, just like the communication that I have been describing throughout the tutorial, you can actually use the same mechanism for power transfer. And because the same way, if you saw my pathloss part, in the first part of the talk, I said that the pathloss of the capacitive coupling compared with the RF on body is much less. And we are exploiting the same mechanism. So you can actually have less path loss, when you use the body coupling as a mechanism for the power transfer.
So, Dr. Yoo, can you see my screen by chance?
Yeah, I'm seeing it.
And is there a particular slide you would like me to go to?
Oh, yeah. Can you please go to slide 78?
Sure. 78 is supplementary material.
No, that's around 10 pages before the supplementary. I don't know, maybe 5 pages.
So yeah. I'll go slowly
looks
here.
Like this is my. This is not the latest slide in my opinion. So let me try to see if I can share my. Okay. I think we can also go to the other slide. Let me see. Okay. I'll try to figure out if there's a slide that I can. It's not ideal, but let's go to slide 13.
Slide 13. Oh. This slide right here?
Yeah, there. So if you look at the graph on your right, lower right, it's not the measurement base, it's a conceptual graph, but I'll say it actually tells you the concept. So if you measure the path loss of the ISM band on a human body, the key point here is on the human body, not the free space, versus the capacitive-based coupling on the human body communication. So you'll see that the path loss on the body coupling is much less compared with the RF on body. And as I said, on top of this, if you have the RF-based transmission, whether it being the communication or power transfer, you have to have an, I'll say, antenna. And if the antenna is in the vicinity of the body, the radiation pattern will be also affected. And that adds around 10 to 15 dB additional path loss. So that's why I mentioned the slide 78 that I presented showed that you can exploit the same body coupling to actually transmit power. Because if you just rely on the RF-based transfer, the human body will work as a blockage. But you can exploit the human body as a coupling medium, then you can collect more power. So that's what I meant.
Interesting. Okay. Very good. Now let's see. There is a question out here. Okay. Let's see. No, I have one because
Okay, I started to share my screen. I found a way to install the extension for sharing my screen. I hope you can see my screen here.
yes, we can see your screen.
Okay, so I'm going back to just to complement what I said. Okay, here we go. Okay, let me just complement my answer. So I would say that if you look at the 2.4 gigahertz as an example, in free space, there's path loss depending on distance. And then if you attach it onto the body, there will be additional path loss due to the human body. And if there's a line of sight, then you see the green line. But if there's no line of sight, the human body will be significantly eating up that RF energy. And that's why you see this red color. There's a huge path loss when the human body is actually blocking the transmitter and the receiver. And if you look at the left diagram here, the gray colored space is the dead zone. If you have a TX power of around 0 dB, then the gray shaded area, you cannot receive any power. So that's one thing. But if you actually use the human body coupling that I have been describing for communication, but as I said, you can actually use that for power transfer as well, then all of a sudden this path loss is much less compared with the RF on body. Therefore, you can utilize this for power transfer mechanism as well. And the last video that I showed is actually exploiting it with the some off-the-shelf components plus some custom ICs. I hope that clarifies.
That does. Thank you very much. Okay, so I was struggling a little bit with the Q&A list, but now I've got it under control. There is a question for the power body coupling scheme. What applications would highly benefit from this method versus what applications would this be detrimental for?
That's right. Oh, okay. That's also a very good question. I would say the most probable application, I would say benefiting application I'll be looking forward to in the coming years will be anything that's related to charging the battery. So such as Fitbit or the watches that has to be attached to your body anyway. And if you can actually charge the battery through this scheme, I didn't mention it in detail here, but you can also harvest energy through the body coupling, and that will extend the battery lifetime. Right now, the efficiency is not that high, but down the line, we are trying our best to improve that power harvesting efficiency as well as transfer efficiency. So my, let's say, very simple answer here is that wearables, especially around your wrist or in a chest, for example, if you are trying to harvest or transfer energy from surroundings, let's say harvesting for sake, if you're trying to harvest energy to your patch that is attached in your chest underneath your clothing, then you're in trouble because the PVs don't work, and the thermal-based harvesters also don't work well in that such conditions because there's not much difference in the thermal. Whereas this type of application has less limitations with regards to the position attached to the body. So I would say benefiting applications would be something that is seriously impacted by the conventional ways, in a way that if you have a line of sight limitation or any blockage due to the environmental changes, whether it being the clothing or the coupling, whatever it is, that will be benefiting. And one example, as I said, is the wearable sensors, such as patches underneath your body, or smart watches and so forth. Now, what is the downside? If you gain something, you also lose something. Here right now, the downside is that the efficiency in terms of power transfer is still not as good as using the battery itself. So for example, if you're transmitting power, the version that we have right now, if you transmit the 3 milliwatt power, what you can cover at the other side of your body, let's say from hand to the ankle, will be around tens of microwatts. So the power transfer efficiency, if you just purely look at the point of view of the power transfer efficiency, is very, very low. So if you try to power up this device 24/7, let's say Fitbit from your cell phone, as of now, probably the efficiency is not that high. But I expect this will improve over time. And I think this is providing one possible way to power up the devices around your body. So we'll see how it goes.
Yeah, very good. It certainly seems like a exciting and emerging field, that is for sure. And so I think that does it for the questions. And I would like to thank Dr. Yoo one more time for really, it was an excellent presentation. I thought it was very well organized and categorized very clearly. I personally felt like I got a lot out of it. It's not a field that I work in all that much. So I would like to thank him, and we will now. Thank you.